Authored by a veteran chemistry teacher, Abdul Shakur, these two textbooks provide all the essentials that would not only enable students to master grade 11 chemistry, but to excel at the next higher level in this subject. What make these texts unique are their creativity and profundity with which concepts are explained for clarity and mastery. The following is one of a set of 44 different tutorials created by the author, using materials primarily from the text Chemistry 11 in Focus. I hope you enjoyed this video. If you liked it, please give it a thumbs up and don't forget to subscribe. We will see you in the next video and thank you for watching.
Today we're dealing with double displacement reaction. And our lesson starts from page 104 and it ends on page 108 from the text, Chemistry 11 in Focus. And we'll be looking at these concepts here: precipitate formation, solubility and dissolubility chart, and how we predict whether or not a precipitate will form when you mix two reagents together. What is a double displacement reaction? In a double displacement reaction, the cation of one ionic compound exchanges place with the cation of another aqueous ionic compound. And double displacements can be represented generally as follows. Using letters of the alphabet, we can represent one of the aqueous ionic compounds as AB and the one here as CD. So we're mixing two of these compounds here. And A represents the cation, or the metallic ion, and this one here is the anion. C, cation, the anion. When these exchange place, what is happening really is that this cation here is taking the place of that one there, and this one here is taking the place of that one there. So we're saying this guy is going across, and this one is coming across that side here. And what do they form? You get AD and CB. So a new compound is formed here, and new compound is formed here. It can also be represented by these models here. If that represented C, and that represented A, and that B and D. If you exchange these two guys, the cations here, you'll end up with these models here. You can see that these are new things that are formed. When you mix two ionic compounds together, one of two things will happen. Either there is no precipitate being formed, or a precipitate being formed, in which case a reaction would have taken place. So we want to show you a scenario here where no precipitate is formed. Here we are having an aqueous solution of sodium chloride and another aqueous solution of potassium nitrate. And we will mix these together and observe whether a precipitate is formed. Now, just want to tell you a little bit more about the aqueous solution. If you have some solid sodium chloride, say in a spatula, and you drop that in water, what happens is that the water causes these ions to separate from each other. It is not really accurate as it is shown here. Here you're seeing that both of the ions are together for the sake of balancing this equation. When in effect what really is happening, all of these ions are floating around in the water like this here, see? And you have trillions and trillions of these are floating around inside the water there. They're kept afloat because of the water molecules inside. What will happen inside here when you mix these two? If you had a bigger beaker and you pour this one into that or that one into that, you'll be allowing this potassium here to move and exchange place with this sodium here, okay? And in so doing, you form these new arrangements here, that one there and that one there. Why this one here would not form a precipitate? Because all the products here are soluble. They is dissolved in water. If this guy here was not soluble in water, then it would have come down as a precipitate. When the products are both soluble in water, right, in this case, no precipitate forms, and therefore you won't see a reaction. So we would say that this represents a double displacement reaction because we did not get any chemical change here. Now if you look here now, one where there is a precipitate being formed. In this reaction here, we're seeing how the potassium ion here is exchanging place with this silver ion here, the cation. And what is formed? You get potassium nitrate being formed and silver iodide. Alright? These react to form a precipitate. This silver iodide here, that's a precipitate. So we say that this represents a double displacement reaction. One of the analogies I like to use to represent a double displacement reaction is people dancing in a party. Let's go back to this one here. Let us suppose that these are friends and they came to a party and they're dancing together. But they're not embracing each other. They're not touching each other. So they're standing in front of each other and they're dancing. Same thing is happening here. These ions are separate from each other. They're dancing, but they're not touching each other. Now, when they exchange cations, these guys keep dancing too. They're dancing in front of each other. They do not embrace. They do not love each other so much to embrace. Same thing is happening here. Unlike what is happening here, something different happens here, right? Look, they're dancing, they're dancing, they're dancing, they're dancing. Now you pour these together. So this guy says, why don't we change friends? So the silver now, the silver goes across there, okay? And your friend potassium comes over there. And look what happens. The potassium and the nitrate, they still keep dancing. They're not touching each other here. Love is not great here. But look what happens here. The moment silver and iodide ion start to dance, look, they start to embrace. The love is great here. The affinity for each other is great. The force of attraction between these is high, unlike these where it is poor. And that is why these ions will combine together here to form something that is insoluble in water, and you get this, all of these here we form as a big chunk of precipitate here, and it will sink to the bottom because silver iodide is not soluble in water. And this is how a precipitate forms. This paragraph here deals with why something forms a precipitate and why one does not form. It has to do with the force of attraction between these two ions here. In this situation here before, there was not a great force of attraction between the silver and the nitrate, nor in this case here. But when you allow this to mix, you're bringing new combinations now where different affinities happen. This one is having a strong affinity for that one there, and that's why this one here will form a precipitate. Reason why this happens is because silver iodide, the bonds here are very, very strong, and the water molecules are not capable of separating these two away from each other. Whereas if you have some potassium nitrate crystals and pour them in water, they separate very easily because it is easy to separate the potassium from the nitrate, unlike the silver iodide. The lattice here is very, very stable, so water molecules cannot come in between these ions here to separate them to make it dissolve. Some sparingly soluble substances can become soluble at a higher temperature. So you can read this paragraph here. Okay, I don't have to read too well to you. You read better, so take your time, go through that there and see why some things dissolve in water easily and why some don't. We'll discuss this when we do solutions in some more detail. All right. How can we predict whether or not when you mix aqueous solutions of two ionic compounds, a precipitate will form? Pay attention to this. This column here represents anions. two other columns here, column 2 and column 3, they represent cations. This one here, column 2 or group 2, will give you examples of cations that will form precipitates with the anions on their extreme left. They're giving you 4 cations here. In this case, any one of these, if they combine with another aqueous solution that has any of these, they will form precipitate. For example, if I mix silver nitrate with, say, sodium chloride, this silver will react with the chloride ion here to form silver chloride. Lead-2 and chloride, lead-2 chloride. Tellurium and this guy and iodide there, it will give you a precipitate. Now what happens across there? Across here, these metal ions here do not form precipitates when they encounter these guys here. Let us say I wanted to know if potassium chloride will form a precipitate, okay? I look for chloride, chloride is here. Is potassium here? No, potassium is not here. It's over this side here. So definitely potassium chloride will not form a precipitate. It will stay as a solution. It will dissolve, okay? So that's row 1. Row 2. Now watch what happens. All cations will form insoluble hydroxides with these. So all cations will form as precipitate if they come in contact with this guy here, except these here. So if you wanted to know if copper 2 will form a precipitate with hydroxide, check here. Is copper 2 there? No. It means if it is not here, it must be in this column here. I can see here, it does form a precipitate here, copper 2 hydroxide here. If I wanted to know if strontium will form a precipitate, I check here to see if strontium is present. Yeah, look, strontium is there. So when strontium combines with OH, it will form a soluble compound. It wouldn't form a precipitate. If I wanted to know, say, zinc, would zinc form a precipitate with OH ions? I check here. Is zinc here? No, zinc is not here. Therefore, it belongs to this group which says all the rest will form a precipitate with this one. Let's come to sulfate now. Any one of these here, if they encounter a sulfate ion, like when you mix them, and the other partner has a sulfate ion, hey, they will form precipitate. For example, barium reacts with sulfate to form a precipitate. I want to know whether or not sodium sulfate is formed during the double displacement reaction, whether or not they form precipitate. I check here to see if it is soluble or not. If it is not amongst these, then it must be here where you find soluble compounds, soluble sulfates. So you do it by elimination. Look where they give you one set, and if that thing is not there, it must belong to the other set. Same thing here, you have all of these guys here. So most cations will form precipitates with these anions, except those on the right. These will not form precipitates when they encounter these ions here. So see, if I wanted to know if barium will form it, yes, barium is not here. So barium forms barium sulfate. Magnesium is not here. Magnesium forms magnesium carbonate. Okay? And so on, and phosphate. So if I wanted to know if potassium will form a precipitate with these, I check here. Is potassium there? Yes. It will not form that. If I wanted to know if copper is going to form a precipitate, copper is not here. Definitely copper will react with any one of these to form a precipitate here. Sulfide. See? All cations will form precipitates with sulfide ions except those on the right. Ammonia and these here. So these are groups 1 and 2A of the periodic table. So if I want to know if a magnesium will form precipitate, magnesium in group 2A. C, if it is here yet, it is here. It wouldn't form a precipitate. If I want to know if zinc will form a precipitate with this, yes, Zinc is not in these here. And here you have acetates. All the metal ions will form soluble acetates. So all metal ions will form soluble acetates, except silver is soluble. All nitrates are soluble. So if you wanted to ensure that you get a salt that dissolves in water, check for the nitrate. Any nitrate will dissolve in water. Just sample of it and quickly dissolves in water. That is how you predict whether or not a precipitate will form, okay? These are some steps I want you to go through when you do your double displacement reaction. These are aqueous compounds here, and you're mixing them, all right? You want to predict whether or not you'll get a precipitate. So you start with aqueous compounds. You know they're all soluble. When you take your magnesium and you will exchange it with that guy there, and then you take your sodium and you exchange it down there, okay? All right, here now we have a new combination now. You're forming sodium chloride here and magnesium carbonate here, okay? You see what I did? I didn't put in any sign here yet. I didn't say it's aqueous. I didn't say it's solid, right? Don't do that for now because you do not know the solubility of those things here, all right? Okay. Mixing is, take these guys each and separate them into their component ions here. Sodium will give you sodium ion here and down there, okay? Magnesium carbonate will give me magnesium ions and carbonate ions. Now you go to your solubility chart and you check the solubility of these two guys. Now what you look for is the anion that is present. If you go to a solubility chart, you see chloride is in the first row on the left hand side. But then you'll be given 4 of these. These here will form insoluble chloride. Is sodium there? Sodium is not there, so sodium must be on this side here. So you'll say that sodium chloride will not form a precipitate. Now you go and you see whether or not magnesium carbonate is soluble. So go to the chart and see where carbonate is. Sorry, carbonate is here. Now all these are soluble. Go where you have the fewer number. Check see if magnesium is amongst these. Is magnesium here? No, magnesium is not here. Okay? So magnesium must be over here. And therefore magnesium will form a precipitate with carbonate. So this is it. To determine the solubility of this one, inspect row 1, column 1 where chloride is. We just did that. And then inspect column 2, row 1, see if some is present. Since sodium is absent from that insoluble one, it must belong to column 3 where we said sodium chloride is now soluble. And we determine magnesium carbonate, same thing. Inspect row 4, column 1 where carbonate is located. Then inspect column 3 of row 4 to see if magnesium is present there. That guy there must be insoluble in water. So magnesium. Magnesium carbonate is thus insoluble in water and it will form a precipitate. Okay, so you rewrite your equation now where you put this as aqueous and that being a solid there, and that's a precipitate. Okay, they will then ask you to do the net ionic equation. So break these down into respective cations and anions. This one here, that one there, over here. You do not trouble the precipitate, as I said before, because these are not broken down into ions. They're insoluble particles, so they don't make ions in water. Then you take out the spectator ions now. This one is chloride ions are spectator ions here. Common both sides here. So let's go on both sides. When you remove those, you end up with only magnesium ion reactor carbonate ions to give you this guy here. So effectively, this is what is happening. So that is double displacement reaction where precipitate is formed. Learn how to do the solubility chart and you'll be in good company. Now you have some reactions here where water is formed You do not get a precipitate, but water is produced. And this happens in a neutralization reaction. Here you're getting a base reacting with an acid here, and this is what happens here. All right? This is how the exchange takes place. So you end up with sodium chloride and water. The hydrogen ions and the OH ion will form a bond there, and you get water. So water is being formed here. But you will not see that as a precipitate, but you can know if this is happening by two means. One, you can put a thermometer inside the beaker where the reaction is taking place, and you can also put a pH meter inside, and you'll see that there will be a change in pH here. This is acidic here, that is basic here. When you mix it all together and you put your pH meter inside there, check the pH of that is going to be neutral. So you get in a salt and water there. There is another type of double displacement reaction where you get a gas is being produced. In this case, if you have hydrochloric acid reacting with a carbonate here, you get sodium chloride and carbonic acid being formed. Carbonic acid, being a weak acid, quickly decomposes to give you carbon dioxide and water. Same thing you see when you have vinegar reacting with baking powder at home, right? So this is what happens. The effervescence is because of the carbon dioxide that is produced there. Okay, another one here. If you take ammonium salts and you react it with a strong base, say potassium hydroxide, it produces potassium chloride. You have the exchange taking place here. That goes there, and that one comes there. Okay, so you end up with ammonium hydroxide here. But this again, just like your friend boric acid, it decomposes very quickly to give you ammonia gas and water there. So when the reaction takes place, you'll have a pungent smell of ammonia, all right? And you can smell that. Okay? Ammonia is produced. What we're saying is that when the ammonium hydroxide is formed, it quickly decomposes into ammonia gas and water there. This ammonia can be identified by its pungent smell and its ability to turn damp pink litmus paper blue. So if you want to check that ammonia is coming out, take a piece of pink litmus paper, damp it, and you put it over the tissue where the reaction is taking place, and you'll see that it will go blue. What I have here is an assignment for students to do. We have two sets of reagents across here, and reagents down this side here, down this group here. So what I would normally do, I have all these in small files, so students will use a spotting plate, and they will react each one of these here, like copper 2 chloride will be reacting with all of these across here, and they'll make observations. And based on what they see, it will indicate whether or not a double displacement reaction happens. Same thing we've done for all of these here. But before they do that, they'll have to separate these into their respective ions. I've done a few for you. Like barium nitrate, these are the two ions that will come on barium nitrate. And the same thing they'll have to do here. I have done a few examples there. So this one here is potassium sulfate. So you have potassium ions and sulfate ions. Now these are your reagents. You put them in an equation. You do your crisscross. Then you use a solubility table to predict whether or not a precipitate will form. If you recognize as an acid-base one, you won't see a precipitate. You will experience some energy change or a change in the pH of the solution. So going back to this one here, you're going to have barium sulfate here and potassium nitrate. Know that all nitrates are soluble, so you need not look up the solubility of any nitrate, you know. But now you have barium sulfate to check. When you check for this, where sulfate is in the solubility chart there, you see that barium is not on the right-hand side. Okay, so it's not something that is soluble. It's not in the right column there, so it must be in the second column there is a nice assignment to do. If you want to check yourself out, you make all these ions there. There's a zinc ion, zinc Zn2, I1, and stuff like that, okay? And then you do the same thing across here. You do the same thing. I did a few here for you. And then you can, lots of practice you have here, you can do all of those here. All right, so that was double displacement reaction. And I hope that was helpful for you. And this is, of course, an example of a double displacement reaction that was photographed. Here is nil nitrate reacting with potassium iodide. When you check here, you go your iodide ion in the table, first row, and then you can see the presence of lead in the middle column there. And of course, you know you're going to get a precipitate there. Very brilliant, nice yellow precipitate of lead iodide there. Okay? And this, of course, is your net ionic equation. Lead, nitrate, potassium iodide. These are all the ions there. These are the ions there. You do not do this because this is a precipitate. That one is soluble. Nitrate ion, common, this, that. And of course, essentially what is reacting are lead ions, lead-2 ions with iodide ions, and that was the precipitate. I hope that was helpful.